in January 2024. ARC-C Heliswag MMLU Truthful QA Wino Grande GSM 8K ARC-C 1. 00000. 4812 0. 8672 0. 4809 0. 8856 0. 7438 Heliswag 0. 4812 1. 00000. 6105 0. 4809 0. 4842 0. 3547 MMLU 0. 8672 0. 6105 1. 00000. 5507 0. 9011 0. 7936 Truthful QA 0. 4809 0. 4228 0. 5507 1. 00000. 4550 0. 5009 Wino Grande 0. 8856 0. 4842 0. 9011 0. 4551. 00000. 7979 GSM 8K 0. 7438 0. 3547 0. 7936 0. 5009 0. 7979 1. 0000. The results from all the selected benchmarks need to be aggregated to rank models. As of this writing, Hugging Face averages a model scores on all these benchmarks to get the final score to rank that model. Averaging means treating all benchmark scores equally, i.e., treating an 80% score on Truthful QA the same as an 80% score on GSM 8K, even if an 80% score on Truthful QA might be much harder to achieve than an 80% score on GSM 8K. This also means giving all benchmarks the same weight, even if, for some tasks, truthfulness might weigh a lot more than being able to solve grade school math problems. Helm authors, on the other hand, decided to shun averaging in favor of mean win rate, which they defined as the fraction of times a model obtains a better score than another model, averaged across scenarios. While public leaderboards are useful to get a sense of models' broad performance, it's important to understand what capabilities a leaderboard is trying to capture. A model that ranks high on a public leaderboard will likely, but far from always, perform well for your application. If you want a model for code generation, a public leaderboard that doesn't include a code generation benchmark might not help you as much. Custom leaderboards with public benchmarks. When evaluating models for a specific application, you're basically creating a private leaderboard that ranks models based on your evaluation criteria. The first step is to gather a list of benchmarks that evaluate the capabilities important to your application. If you want to build a coding agent, look at code-related benchmarks. If you build a writing assistant, look into creative writing benchmarks. As new benchmarks are constantly introduced and old benchmarks become saturated, you should look for the latest benchmarks. Make sure to evaluate how reliable a benchmark is. Because anyone can create and publish a benchmark, many benchmarks might not be measuring what you expect them to measure. Model selection 195. 24 Reading about other people's experience is educational, but it's up to us to discern an anecdote from the universal truth. The same model update can cause some applications to degrade and some to improve. For example, migrating from GPT-3 5 Turbo 0301 to GPT-3 5 Turbo 1106 led to a 10% drop in voice flow's intent classification task but an improvement in GoDaddy's customer support chatbot. Are OpenAI's models getting worse? Every time OpenAI updates its models, people complain that their models seem to be getting worse. For example, a study by Stanford and UC Berkeley, Chen et al., 2023, found that for many benchmarks, both GPT-3 5 and GPT-4's performances changed significantly between March 2023 and June 2023, as shown in Figure 4.9. Figure 4.9. Changes in the performances of GPT-3. 5 and GPT-4 from March 2023 to June 2023 on certain benchmarks, Chen et al., 2023. Assuming that OpenAI doesn't intentionally release worse models, what might be the reason for this perception? One potential reason is that evaluation is hard, and no one, not even OpenAI, knows for sure if a model is getting better or worse. While evaluation is definitely hard, I doubt that OpenAI would fly completely blind. 24. If the second reason is true, it reinforces the idea that the best model overall might not be the best model for your application. 196, Chapter 4, Evaluate AI Systems. 25. If there is a publicly available score, check how reliable the score is. 26. The Helm paper reported that the total cost is $38,000 for commercial APIs and 19,500 GPU hours for open models. If an hour of GPU costs between $2.15 and $3.18, the total cost comes out to $80,000 to $100,000. Not all models have publicly available scores on all benchmarks. If the model you care about doesn't have a publicly available score on your benchmark, you will need to run the evaluation yourself. 25. Hopefully, an evaluation harness can help you with that. Running benchmarks can be expensive. For example, Stanford spent approximately $80,000 to $100,000 to evaluate 30 models on their full Helm suite. 26. The more models you want to evaluate and the more benchmarks you want to use, the more expensive it gets. Once you've selected a set of benchmarks and obtained the scores for the models you care about on these benchmarks, you then need to aggregate these scores to rank models. Not all benchmark scores are in the same unit or scale. One benchmark might use accuracy, another F1, and another BLEU score. You will need to think about how important each benchmark is to you and weigh their scores accordingly. As you evaluate models using public benchmarks, keep in mind that the goal of this process is to select a small subset of models to do more rigorous experiments using your own benchmarks and metrics. This is not only because public benchmarks are unlikely to represent your application's needs perfectly, but also because they are likely contaminated. How public benchmarks get contaminated and how to handle data contamination will be the topic of the next section. Data contamination with public benchmarks. Data contamination is so common that there are many different names for it, including data leakage, training on the test set, or simply cheating. Data contamination happens when a model was trained on the same data it's evaluated on. If so, it's possible that the model just memorizes the answers it saw during training, causing it to achieve higher evaluation scores than it should. A model that is trained on the MMLU benchmark can achieve high MMLU scores without being useful. Ryland Schaefer, a PhD student at Stanford, demonstrated this beautifully in his 2023 satirical paper, Pre-training on the test set is all you need. By training exclusively on data from several benchmarks, his 1 million parameter model was able to achieve near-perfect scores and outperformed much larger models on all these benchmarks. Model selection, 197. 27. A friend quipped, a benchmark stops being useful as soon as it becomes public. How data contamination happens. While some might intentionally train on benchmark data to achieve misleadingly high scores, most data contamination is unintentional. Many models today are trained on data scraped from the internet, and the scraping process can accidentally pull data from publicly available benchmarks. Benchmark data published before the training of a model is likely included in the model's train-ing data. 27. It's one of the reasons existing benchmarks become saturated so quickly, and why model developers often feel the need to create new benchmarks to evaluate their new models. Data contamination can happen indirectly, such as when both evaluation and train-ing data come from the same source. For example, you might include math textbooks in the training data to improve the model's math capabilities, and someone else might use questions from the same math textbooks to create a benchmark to evaluate the model's capabilities. Data contamination can also happen intentionally for good reasons. Let's say you want to create the best possible model for your users. Initially, you exclude benchmark data from the model's training data and choose the best model based on these benchmarks. However, because high-quality benchmark data can improve the model's performance, you then continue training your best model on benchmark data before releasing it to your users. So the released model is contaminated, and your users won't be able to evaluate it on contaminated benchmarks, but this might still be the right thing to do. Handling data contamination. The prevalence of data contamination undermines the trustworthiness of evaluation benchmarks. Just because a model can achieve high performance on bar exams doesn't mean it's good at giving legal advice. It could just be that this model has been trained on many bar exam questions. To deal with data contamination, you first need to detect the contamination, and then decontaminate your data. You can detect contamination using heuristics like n-gram overlapping and perplexity. N-gram overlapping, for example, if a sequence of 13 tokens in an evaluation sample is also in the training data, the model has likely seen this evaluation sample during training. This evaluation sample is considered dirty. Perplexity. Recall that perplexity measures how difficult it is for a model to predict a given text. If a model's perplexity on evaluation data is unusually low, meaning the 198, Chapter 4, Evaluate AI Systems model can easily predict the text, it's possible that the model has seen this data before during training. The n-gram overlapping approach is more accurate but can be time-consuming and expensive to run because you have to compare each benchmark example with the entire training data. It's also impossible without access to the training data. The perplexity approach is less accurate but much less resource-intensive. In the past, ML textbooks advised removing evaluation samples from the training data. The goal is to keep evaluation benchmarks standardized so that we can compare different models. However, with foundation models, most people don't have control over training data. Even if we have control over training data, we might not want to remove all benchmark data from the training data, because high-quality benchmark data can help improve the overall model performance. Besides, there will always be benchmarks created after models are trained, so there will always be contaminated evaluation samples. For model developers, a common practice is to remove benchmarks they care about from their training data before training their models. Ideally, when reporting your model performance on a benchmark, it's helpful to disclose what percentage of this benchmark data is in your training data, and what the model's performance is on both the overall benchmark and the clean samples of the benchmark. Sadly, because detecting and removing contamination takes effort, many people find it easier to just skip it. OpenAI, when analyzing GPT-3's contamination with common benchmarks, found 13 benchmarks with at least 40% in the training data, Brown et al., 2020. The relative difference in performance between evaluating only the clean sample and evaluating the whole benchmark is shown in Figure 4.10. Figure 4.10. Relative difference in GPT-3's performance when evaluating using only the clean sample compared to evaluating using the whole benchmark. Model selection 199. To combat data contamination, leaderboard hosts like Hugging Face plot standard deviations of models' performance on a given benchmark to spot outliers. Public benchmarks should keep part of their data private and provide a tool for model developers to automatically evaluate models against the private holdout data. Public benchmarks will help you filter out bad models, but they won't help you find the best models for your application. After using public benchmarks to narrow them to a set of promising models, you'll need to run your own evaluation pipeline to find the best one for your application. How to design a custom evaluation pipeline will be our next topic. Design your evaluation pipeline. The success of an AI application often hinges on the ability to differentiate good outcomes from bad outcomes. To be able to do this, you need an evaluation pipeline that you can rely upon. With an explosion of evaluation methods and techniques, it can be confusing to pick the right combination for your evaluation pipeline. This section focuses on evaluating open-ended tasks. Evaluating close-ended tasks is easier, and its pipeline can be inferred from this process. Step 1. Evaluate all components in a system. Real-world AI applications are complex. Each application might consist of many components, and a task might be completed after many turns. Evaluation can happen at different levels, per task, per turn, and per intermediate output. You should evaluate the end-to-end output and each component's intermediate output independently. Consider an application that extracts a person's current employer from their resume PDF, which works in 2 steps. 1. Extract all the text from the PDF. 2. Extract the current employer from the extracted text. If the model fails to extract the right current employer, it can be because of either step. If you don't evaluate each component independently, you don't know exactly where your system fails. The first PDF to text step can be evaluated using similarity between the extracted text and the ground truth text. The second step can be evaluated using accuracy. Given the correctly extracted text, how often does the application correctly extract the current employer? If applicable, evaluate your application both per turn and per task. A turn can consist of multiple steps and messages. If a system takes multiple steps to generate an output, it's still considered a turn. 200 Chapter 4 Evaluate AI Systems. Generative AI applications, especially chatbot-like applications, allow back and forth between the user and the application, as in a conversation, to accomplish a task. Imagine you want to use an AI model to debug why your Python code is failing. The model responds by asking for more information about your hardware or the Python version you're using. Only after you've provided this information can the model help you debug. Turn-based evaluation evaluates the quality of each output. Task-based evaluation evaluates whether a system completes a task. Did the application help you fix the bug? How many turns did it take to complete the task? It makes a big difference if a system is able to solve a problem in 2 turns or in 20 turns. Given that what users really care about is whether a model can help them accomplish their tasks, task-based evaluation is more important. However, a challenge of task-based evaluation is it can be hard to determine the boundaries between tasks. Imagine a conversation you have with ChatGPT. You might ask multiple questions at the same time. When you send a new query, is this a follow-up to an existing task or a new task? One example of task-based evaluation is the 20_questions benchmark, inspired by the classic game 20 questions, in the Big Bench benchmark suite. One instance of the model, Alice, chooses a concept, such as apple, car, or computer. Another instance of the model, Bob, asks Alice a series of questions to try to identify this concept. Alice can only answer yes or no. The score is based on whether Bob successfully guesses the concept, and how many questions it takes for Bob to guess it. Here's an example of a plausible conversation in this task, taken from the Big Bench's GitHub repository. Bob, is the concept an animal? Alice, no. Bob, is the concept a plant? Alice, yes. Bob, does it grow in the ocean? Alice, no. Bob, does it grow in a tree? Alice, yes. Bob, is it an apple? Bob's guess is correct, and the task is completed. Design your evaluation pipeline. 201. Step 2. Create an evaluation guideline. Creating a clear evaluation guideline is the most important step of the evaluation pipeline. An ambiguous guideline leads to ambiguous scores that can be misleading. If you don't know what bad responses look like, you won't be able to catch them. When creating the evaluation guideline, it's important to define not only what the application should do, but also what it shouldn't do. For example, if you build a customer support chatbot, should this chatbot answer questions unrelated to your product, such as about an upcoming election? If not, you need to define what inputs are out of the scope of your application, how to detect them, and how your application should respond to them. Define evaluation criteria often. The hardest part of evaluation isn't determining whether an output is good, but rather what good means. In retrospect of 1 year of deploying generative AI applications, LinkedIn shared that the first hurdle was in creating an evaluation guideline. A correct response is not always a good response. For example, for their AI-powered job assessment application, the response "you are a terrible fit" might be correct but not helpful, thus making it a bad response. A good response should explain the gap between this job's requirements and the candidate's background, and what the candidate can do to close this gap. Before building your application, think about what makes a good response. Langchain State of AI 2023 found that, on average, their users use 3 different types of feedback criteria to evaluate an application. For example, for a customer support application, a good response might be defined using 3 criteria. 1. Relevance. The response is relevant to the user's query. 2. Factual consistency. The response is factually consistent with the context. 3. Safety. The response isn't toxic. To come up with these criteria, you might need to play around with test queries. I'd ally real user queries. For each of these test queries, generate multiple responses, either manually or using AI models, and determine if they are good or bad. Create scoring rubrics with examples for each criterion. Choose a scoring system. Would it be binary, 0 and 1, from 1 to 5, between 0 and 1, or something else? For example, to evaluate whether an answer is consistent with a given context, some teams use a binary scoring system, 0 for factual inconsistency and 1 for factual consistency. Some teams use 3 values, -1 for contradiction, 1 for entailment, and 0 for neutral. Which scoring system to use depends on your data and your needs. 202, Chapter 4, Evaluate AI Systems. On this scoring system, create a rubric with examples. What does a response with a score of 1 look like and why does it deserve a 1? Validate your rubric with humans, yourself, coworkers, friends, etc. If humans find it hard to follow the rubric, you need to refine it to make it unambiguous. This process can require a lot of back and forth, but it's necessary. A clear guideline is the backbone of a reliable evaluation pipeline. This guideline can also be reused later for training data annotation, as discussed in Chapter 8. Tie evaluation metrics to business metrics within a business. An application must serve a business goal. The application's metrics must be considered in the context of the business problem it's built to solve. For example, if your customer support chatbot's factual consistency is 80%, what does it mean for the business? For example, this level of factual consistency might make the chatbot unusable for questions about billing but good enough for queries about product recommendations or general customer feedback. Ideally, you want to map evaluation metrics to business metrics, to something that looks like this: factual consistency of 80%, we can automate 30% of customer support requests. Factual consistency of 90%, we can automate 50%. Factual consistency of 98%, we can automate 90%. Understanding the impact of evaluation metrics on business metrics is helpful for planning. If you know how much gain you can get from improving a certain metric, you might have more confidence to invest resources into improving that metric. It's also helpful to determine the usefulness threshold. What scores must an application achieve for it to be useful? For example, you might determine that your chatbot's factual consistency score must be at least 50% for it to be useful. Anything below this makes it unusable even for general customer requests. Before developing AI evaluation metrics, it's crucial to first understand the business metrics you're targeting. Many applications focus on stickiness metrics, such as daily, weekly, or monthly active users, DAU, WAU, MAU. Others prioritize engagement metrics, like the number of conversations a user initiates per month or the duration of each visit. The longer a user stays on the app, the less likely they are to leave. Choosing which metrics to prioritize can feel like balancing profits with social responsibility. While an emphasis on stickiness and engagement metrics can lead to higher revenues, it may also cause a product to prioritize addictive features or extreme content, which can be detrimental to users. Design your evaluation pipeline. 203. Step 3. Define evaluation methods and data. Now that you've developed your criteria and scoring rubrics, let's define what methods and data you want to use to evaluate your application. Select evaluation methods. Different criteria might require different evaluation methods. For example, you use a small, specialized toxicity classifier for toxicity detection, semantic similarity to may assure relevance between the response and the user's original question, and an AI judge to measure the factual consistency between the response and the whole context. An unambiguous scoring rubric and examples will be critical for specialized scorers and AI judges to succeed. It's possible to mix and match evaluation methods for the same criteria. For example, you might have a cheap classifier that gives low-quality signals on 100% of your data, and an expensive AI judge to give high-quality signals on 1% of the data. This gives you a certain level of confidence in your application while keeping costs manageable. When log probes are available, use them. Log probes can be used to measure how confident a model is about a generated token. This is especially useful for classification. For example, if you ask a model to output one of the 3 classes and the model's log probes for these 3 classes are all between 30 and 40%, this means the model isn't confident about this prediction. However, if the model's probability for one class is 95%, this means that the model is highly confident about this prediction. Log probes can also be used to evaluate a model's perplexity for a generated text, which can be used for measurements such as fluency and factual consistency. Use automatic metrics as much as possible, but don't be afraid to fall back on human evaluation, even in production. Having human experts manually evaluate a model's quality is a long-standing practice in AI. Given the challenges of evaluating open-ended responses, many teams are looking at human evaluation as the North Star metric to guide their application development. Each day, you can use human experts to evaluate a subset of your application's outputs that day to detect any changes in the application's performance or unusual patterns in usage. For example, LinkedIn Devil opted a process to manually evaluate up to 500 daily conservations with their AI systems. Consider evaluation methods to be used not just during experimentation but also during production. During experimentation, you might have reference data to compare your application's outputs to, whereas, in production, reference data might not be immediately available. However, in production, you have actual users. Think about what kinds of feedback you want from users, how user feedback correlates to other evaluation metrics, and how to use user feedback to improve your application. How to collect user feedback is discussed in Chapter 10. 204, Chapter 4, Evaluate AI Systems. Annotate evaluation data. Curate a set of annotated examples to evaluate your application. You need annotated data to evaluate each of your system's components and each criterion, for both turn-based and task-based evaluation. Use actual production data if possible. If your apply cation has natural labels that you can use, that's great. If not, you can use either humans or AI to label your data. Chapter 8 discusses AI-generated data. The success of this phase also depends on the clarity of the scoring rubric. The annotation guideline created for evaluation can be reused to create instruction data for fine-tuning later, if you choose to fine-tune. Slice your data to gain a finer-grained understanding of your system. Slicing means separating your data into subsets and looking at your system's performance on each subset separately. I wrote at length about slice-based evaluation in designing machine learning systems, O'Reilly, so here, I'll just go over the key points. A finer-grained understanding of your system can serve many purposes. Avoid potential biases, such as biases against minority user groups. Debug. If your application performs particularly poorly on a subset of data, could that be because of some attributes of this subset, such as its length, topic, or format? Find areas for application improvement. If your application is bad on long inputs, perhaps you can try a different processing technique or use new models that perform better on long inputs. Avoid falling for Simpson's paradox, a phenomenon in which model A performs better than model B on aggregated data but worse than model B on every subset of data. Table 4:6 shows a scenario where model A outperforms model B on each subgroup but underperforms model B overall. Table 4:6. An example of Simpson's paradox. A group 1 group 2 overall model A 93%, 81/87, 73%, 192/263, 78%, 273 350ths, model B 87%, 234/270, 69%, 55/80ths, 83%, 289/350. I also used this example in designing machine learning systems. Numbers from Charig et al., comparison of treatment of renal calculi by open surgery, percutaneous nephrolithotomy, and extracorporeal shockwave lithotripsy, British Medical Journal, Clinical Research Edition, 292, No. 6524, March 1986 879-82. You should have multiple evaluation sets to represent different data slices. You should have one set that represents the distribution of the actual production data to estimate how the system does overall. You can slice your data based on tiers, paying users versus free users, traffic sources, mobile versus web usage, and more. You can have a set consisting of the examples for which the system is known to frequently design your evaluation pipeline. 205. Make mistakes. You can have a set of examples where users frequently make mistakes. If typos are common in production, you should have evaluation examples that contain typos. You might want an out-of-scope evaluation set, input your apply cation isn't supposed to engage with, to make sure that your application handles them appropriately. If you care about something, put a test set on it. The data curated and annotated for evaluation can then later be used to synthesize more data for training, as discussed in Chapter 8. How much data you need for each evaluation set depends on the application and evaluation methods you use. In general, the number of examples in an evaluation set should be large enough for the evaluation result to be reliable, but small enough to not be prohibitively expensive to run. Let's say you have an evaluation set of 100 examples. To know whether 100 is sufficient for the result to be reliable, you can create multiple bootstraps of these 100 examples and see if they give similar evaluation results. Basically, you want to know that if you evaluate the model on a different evaluation set of 100 examples, would you get a different result? If you get 90% on one bootstrap but 70% on another bootstrap, your evaluation pipeline isn't that trustworthy. Concretely, here's how each bootstrap works. 1. Draw 100 samples, with replacement, from the original 100 evaluation examples. 2. Evaluate your model on these 100 bootstrap samples and obtain the evaluation results. Repeat for a number of times. If the evaluation results vary wildly for different bootstraps, this means that you'll need a bigger evaluation set. Evaluation results are used not just to evaluate a system in isolation but also to compare systems. They should help you decide which model, prompt, or other component is better. Say a new prompt achieves a 10% higher score than the old prompt, how big does the evaluation set have to be for us to be certain that the new prompt is indeed better? In theory, a statistical significance test can be used to compute the sample size needed for a certain level of confidence, e.g., 95% confidence, if you know the score distribution. However, in reality, it's hard to know the true score distribution. 206, Chapter 4, Evaluate AI Systems. 28. This is because the square root of 10 is approximately 3. 3. OpenAI suggested a rough estimation of the number of evaluation samples needed to be certain that one system is better, given a score difference, as shown in Table 4:7. A useful rule is that for every 3 times decrease in score difference, the number of samples needed increases 10 times. 28. Table 4:7. A rough estimation of the number of evaluation samples needed to be 95% confident that one system is better. Values from OpenAI. Difference to detect sample size needed for 95% confidence 30% 10% 103% 10001% 10000 as a reference. Among evaluation benchmarks in a Luther's LM evaluation harness, the median number of examples is 1,000, and the average is 2,159. The organizers of the inverse scaling prize suggested that 300 examples is the absolute minimum and they would prefer at least 1,000, especially if the examples are being synthesized. McKenzie et al., 2023. Evaluate your evaluation pipeline. Evaluating your evaluation pipeline can help with both improving your pipeline's reliability and finding ways to make your evaluation pipeline more efficient. Reliable ITY is especially important with subjective evaluation methods such as AI as a judge. Here are some questions you should be asking about the quality of your evaluation pipeline. Is your evaluation pipeline getting you the right signals? Do better responses indeed get higher scores? Do better evaluation metrics lead to better business outcomes? How reliable is your evaluation pipeline? If you run the same pipeline twice, do you get different results? If you run the pipeline multiple times with different evaluation datasets, what would be the variance in the evaluation results? You should aim to increase reproducibility and reduce variance in your evaluation pipeline. Be consistent with the configurations of your evaluation. For example, if you use an AI judge, make sure to set your judge's temperature to 0. Design your evaluation pipeline. 207. 29. For example, if there's no correlation between a benchmark on translation and a benchmark on math, you might be able to infer that improving a model's translation capability has no impact on its math capability. How correlated are your metrics? As discussed in benchmark selection and aggregation on page 191, if two metrics are perfectly correlated, you don't need both of them. On the other hand, if two metrics are not at all correlated, this means either an interesting insight into your model or that your metrics just aren't trustworthy. 29. How much cost and latency does your evaluation pipeline add to your application? Evaluation, if not done carefully, can add significant latency and cost to your application. Some teams decide to skip evaluation in the hope of reducing latency. It's a risky bet. Iterate as your needs and user behaviors change. Your evaluation criteria will also evolve, and you'll need to iterate on your evaluation pipeline. You might need to update the evaluation criteria, change the scoring rubric, and add or remove examples. While iteration is necessary, you should be able to expect a certain level of consistency from your evaluation pipeline. If the evaluation process changes constantly, you won't be able to use the evaluation results to guide your application's development. As you iterate on your evaluation pipeline, make sure to do proper experiment track ing, log all variables that could change in an evaluation process, including but not limited to the evaluation data, the rubric, and the prompt and sampling configurations used for the AI judges. Summary: this is one of the hardest, but I believe one of the most important, AI topics that I've written about. Not having a reliable evaluation pipeline is one of the biggest blocks to AI adoption. While evaluation takes time, a reliable evaluation pipeline will enable you to reduce risks, discover opportunities to improve performance, and benchmark progresses, which will all save you time and headaches down the line. Given an increasing number of readily available foundation models, for most application developers, the challenge is no longer in developing models but in selecting the right models for your application. This chapter discussed a list of criteria that are often used to evaluate models for applications, and how they are evaluated. It discussed how to evaluate both domain-specific capabilities and generation capabilities, including factual consistency and safety. Many criteria to evaluate foundation models evolved from traditional NLP, including fluency, coherence, and faithfulness. 208 Chapter 4, Evaluate AI Systems. To help answer the question of whether to host a model or to use a model API, this chapter outlined the pros and cons of each approach along 7 axes, including data privacy, data lineage, performance, functionality, control, and cost. This decision, like all the build versus buy decisions, is unique to every team, depending not only on what the team needs but also on what the team wants. This chapter also explored the thousands of available public benchmarks. Public benchmarks can help you weed out bad models, but they won't help you find the best models for your applications. Public benchmarks are also likely contaminated, as their data is included in the training data of many models. There are public leaderboards that aggregate multiple benchmarks to rank models, but how benchmarks are selected and aggregated is not a clear process. The lessons learned from public leaderboards are helpful for model selection, as model selection is akin to creating a private leaderboard to rank models based on your needs. This chapter ends with how to use all the evaluation techniques and criteria discussed in the last chapter and how to create an evaluation pipeline for your application. No perfect evaluation method exists. It's impossible to capture the ability of a high-dimensional system using one or few-dimensional scores. Evaluating modern AI systems has many limitations and biases. However, this doesn't mean we shouldn't do it. Combining different methods and approaches can help mitigate many of these challenges. Even though dedicated discussions on evaluation end here, evaluation will come up again and again, not just throughout the book but also throughout your application development process. Chapter 6 explores evaluating retrieval and agentic systems, while Chapters 7 and 9 focus on calculating a model's memory usage, latency, and costs. Data quality verification is addressed in Chapter 8, and using user feedback to evaluate production applications is addressed in Chapter 10. With that, let's move on to the actual model adaptation process, starting with a topic that many people associate with AI engineering, prompt engineering. Summary 209. In its short existence, prompt engineering has managed to generate an incredible amount of animosity. Complaints about how prompt engineering is not a real thing have gathered thousands of supporting comments, see 1, 2, 3, 4. When I told people that my upcoming book has a chapter on prompt engineering, many rolled their eyes. Chapter 5 Prompt engineering. Prompt engineering refers to the process of crafting an instruction that gets a model to generate the desired outcome. Prompt engineering is the easiest and most common model adaptation technique. Unlike fine-tuning, prompt engineering guides a model's behavior without changing the model's weights. Thanks to the strong base capabilities of foundation models, many people have successfully adapted them for applications using prompt engineering alone. You should make the most out of prompting before moving to more resource-intensive techniques like fine-tuning. Prompt engineering's ease of use can mislead people into thinking that there's not much to it. At first glance, prompt engineering looks like it's just fiddling with words until something works. While prompt engineering indeed involves a lot of fiddling, it also involves many interesting challenges and ingenious solutions. You can think of prompt engineering as human-to-AI communication. You communicate with AI models to get them to do what you want. Anyone can communicate, but not everyone can communicate effectively. Similarly, it's easy to write prompts but not easy to construct effective prompts. Some people argue that prompt engineering lacks the rigor to qualify as an engineering discipline. However, this doesn't have to be the case. Prompt experiments should be conducted with the same rigor as any ML experiment, with systematic experimentation and evaluation. The importance of prompt engineering is perfectly summarized by a research manager at OpenAI that I interviewed. The problem is not with prompt engineering. It's 211. A real and useful skill to have. The problem is when prompt engineering is the only thing people know. To build production-ready AI applications, you need more than just prompt engineering. You need statistics, engineering, and classic ML knowledge to do experiment tracking, evaluation, and dataset curation. This chapter covers both how to write effective prompts and how to defend your applications against prompt attacks. Before diving into all the fun applications you can build with prompts, let's first start with the fundamentals, including what exactly a prompt is and prompt engineering best practices. Introduction to prompting. A prompt is an instruction given to a model to perform a task. The task can be as simple as answering a question, such as who invented the number 0? It can also be more complex, such as asking the model to research competitors for your product idea, build a website from scratch, or analyze your data. A prompt generally consists of one or more of the following parts: task description, what you want the model to do, including the role you want the model to play, and the output format. Examples of how to do this task. For example, if you want the model to detect toxicity in text, you might provide a few examples of what toxicity and non-toxicity look like. The task, the concrete task you want the model to do, such as the question to answer or the book to summarize. Figure 5.1 shows a very simple prompt that one might use for an NER, named entity recognition, task. Figure 5.1. A simple prompt for NER. For prompting to work, the model has to be able to follow instructions. If a model is bad at it, it doesn't matter how good your prompt is, the model won't be able to. 212 Chapter 5, Prompt Engineering. 2 In late 2023, Stanford dropped robustness from their Helm Light benchmark. Follow it. How to evaluate a model's instruction following capability is discussed in Chapter 4. How much prompt engineering is needed depends on how robust the model is to prompt perturbation. If the prompt changes slightly, such as writing 5 instead of 5, adding a new line, or changing capitalization, would the model's response be dramatically different? The less robust the model is, the more fiddling is needed. You can measure a model's robustness by randomly perturbing the prompts to see how the output changes. Just like instruction following capability, a model's robustness is strongly correlated with its overall capability. As models become stronger, they also become more robust. This makes sense because an intelligent model should understand that 5 and 5 mean the same thing. 2 For this reason, working with stronger models can often save you headaches and reduce time wasted on fiddling. Experiment with different prompt structures to find out which works best for you. Most models, including GPT-4, empirically perform better when the task description is at the beginning of the prompt. However, some models, including Llama 3, seem to perform better when the task description is at the end of the prompt. In context learning, zero-shot and few-shot teaching models what to do via prompts is also known as in-context learning. This term was introduced by Brown et al. 2020, in the GPT-3 paper, language models are few-shot learners. Traditionally, a model learns the desirable behavior during training, including pre-training, post-training, and fine-tuning, which involves updating model weights. The GPT-3 paper demonstrated that language models can learn the desirable behavior from examples in the prompt, even if this desirable behavior is different from what the model was originally trained to do. No weight updating is needed. Concretely, GPT-3 was trained for next token prediction, but the paper showed that GPT-3 could learn from the context to do translation, reading comprehension, simple math, and even answer SAT questions. In-context learning allows a model to incorporate new information continually to make decisions, preventing it from becoming outdated. Imagine a model that was trained on the old JavaScript documentation. To use this model to answer questions about the new JavaScript version, without in-context learning, you'd have to retrain this model. Within context learning, you can include the new JavaScript changes in the model's context, allowing the model to respond to queries beyond its cutoff date. This makes in-context learning a form of continual learning. Introduction to Prompting 213. Each example provided in the prompt is called a shot. Teaching a model to learn from examples in the prompt is also called few-shot learning. With 5 examples, it's 5-shot learning. When no example is provided, it's zero-shot learning. Exactly how many examples are needed depends on the model and the application. You'll need to experiment to determine the optimal number of examples for your applications. In general, the more examples you show a model, the better it can learn. The number of examples is limited by the model's maximum context length. The more examples there are, the longer your prompt will be, increasing the inference cost. For GPT-3, few-shot learning showed significant improvement compared to zero-shot learning. However, for the use cases in Microsoft's 2023 analysis, few-shot learn ing led to only limited improvement compared to zero-shot learning on GPT-4 and a few other models. This result suggests that as models become more powerful, they become better at understanding and following instructions, which leads to better performance with fewer examples. However, the study might have underestimated the impact of few-shot examples on domain-specific use cases. For example, if a model doesn't see many examples of the IBIS data frame API in its training data, including IBIS examples in the prompt can still make a big difference. Terminology ambiguity, prompt versus context. Sometimes, prompt and context are used interchangeably. In the GPT-3 paper, Brown et al., 2020, the term context was used to refer to the entire input into a model. In this sense, context is exactly the same as prompt. However, in a long discussion on my Discord, some people argued that context is part of the prompt. Context refers to the information a model needs to perform what the prompt asks it to do. In this sense, context is contextual information. To make it more confusing, Google's Palm 2 documentation defines context as the description that shapes how the model responds throughout the conversation. For example, you can use context to specify words the model can or cannot use, topics to focus